Hi, we were the Coastal Changes team for ICESat-2, and we look specifically at the applications of ICESat-2 and monitoring mangrove forests. My name is Isabella Mazzucca, and I'm a rising senior.
I'm Kenna Bernardin. I'm also a rising senior.
And I'm Devanshi Kaura, and I'm also a rising senior.
So ICESat-2 stands for Ice, Cloud, and Land Elevation Satellite 2, and it was launched in 2018. Its primary purpose is to measure land elevation throughout the Earth, and it does this via the Atlas instrument, which measures travel times of laser pulses as they bounce to and from the Earth back to the instrument.
So specifically, what are mangroves? Mangroves are coastal shrubs and trees that live along the equator in tropical climates, and they're really important for coastal health. So some of the things that they do is they act as a natural barrier against storms. They prevent after storm flooding. They block high winds. They also slow down the rate of coastal erosion, and they also hold a lot of carbon in the root structures that would anyways contribute to greenhouse gases. So our goal is to explore the ability of ICESat-2 and applications of LandSat-8 to discern the impact that large-scale storms or cyclones have on these mangrove forests. So we separated our analyses into qualitative and quantitative, and we are looking for, our hypothesis was that we would see low to no variability in our base year and high to extreme variability in our study year. So our process for the baseline was selecting a region, and we chose the Sundarbans Conservation Forest, which is located in India and Bangladesh. And first of all, we collected images from LandSat-8. We manipulated these images in QGIS, which is a software program. And here we applied NDMI bandmath, which stands for Normalized Difference Moisture Index. And this allows us to see liquid water content within these plants. And then we created a Python script, and this is what gave us our graph outputs. And altogether, we found our average mangrove change over time.
Very briefly, what our script did was that it took a track from the ICESat-2 instrument, and then it queried only the top of Canopy photons from that track. It then split those photons into separate bins of equal length, and then it calculated the average top of Canopy height per bin.
Over here, we have a map of the Sundarbans forest by species. And since it is the largest, most compact mangrove forest in the world, there are a lot of different species. So figure 5, 6, and 7 show the three most prominent species in the forest. The tallest of them being figure 7, which is the Heritiera fomes, which is an average height from 15 to 25 meters tall. And it is the green area on the graph.
And then these are all of the track locations that we used for this study. So they did cover a pretty wide range throughout the forest. And now we will go over what we found for our baseline year.
So for our baseline, the first step was to make sure that there wouldn't be a lot of seasonal variability within these mangroves. And the way that we did this is I calculated the average temperature for all 4 of our study years, 2018 to 2021. And I also calculated our average precipitation levels. What we found is that for 2018 to 2021, there's an average of 70 degrees Fahrenheit to 90 degrees Fahrenheit all year round. And this is a really comfortable region for these mangroves to be in. So we concluded that there wouldn't be a lot of seasonal variability. So this is our 2018 to 2019 analyses, and our average was in the 70s in Fahrenheit.
So to analyze changes in top of canopy height, we separated the forest into 2 major regions. Our first region was the West Sundarbans. As you can see, the graphs represent what I mentioned before, which was that we took the average per bin. So each of those dots that you see on the graph represent 1 bin and its average. As you can tell, for the tracks throughout the year, the averages remained about the same within the same range between 5 and 10 meters. And that's further supported by this date. It was a little farther to the right of the previous 3 tracks, but it also could portray that consistency between around 5 and a little over 7.5 meters. So once again, it was pretty uniform throughout the year. And then taken together, these box plots represent each of those individual dates side by side. As you can see at the bottom of the graph, we did provide the medians. Basically, on these box plots, they represent the median, which is the yellow line, and that's the 50th percentile of the data. And the boxes themselves represent 50% of the data for each range, for each date. And as you can tell, for all 4 of the dates, they were pretty, that 50% was pretty consistent. It lied around 6 and 7 meters. And to quantify this lack of variability between this one species that predominated Western Sundarbans, we found that the total variability was less than 1 meter at 0.741 meters. So pretty, that once again conveys pretty consistent average heights throughout the year.
Over here, we had section 2 of our forest, which is the Central Sundarbans track averages. And again, we sorted them out by location. So in this first batch, I have October of 2018, January of 2019, and August of 2019. And as you can see, within these 3, there is not as much variability. And in each individual track, there isn't much variability either. So this is pretty uniform and a good indicator of a pretty calm year. In my next location batch, I have May of 2019. Over here, we did have some problem with noise, but I'm sure if we had a little more time to work on a script, we could have taken out noise. Other than that, this track is also pretty uniform with the last one. Again, a good indicator of a good baseline. And then my last batch of location was November of 2018 and February of 2019. Over here in our average heights, as you can see towards the end of the bins, there was a shoot up in heights. So at first we thought it was something random, but then we realized that it was not noise either. It was actually a species change. So our taller mangroves actually fell on the end of this track, causing that shoot up in the heights where the gold star is. So now, whenever you look at all these 6 states in comparison, you can see that the ones with the gold stars shoot up way higher. But if you ignore those 2 and look at the other 4, they're very uniform, very similar to each other, and they show very little variability. So we decided to split the variability between species. So in these 4 shorter ones, that's our Cereops species. So the total variability for that species itself is 0.643 meters. For our 2 taller box plots, those are our other 2 species. We calculated the variability within those, and it was 1.997 meters, almost 2 meters, so pretty different. Now over here, we wanted to show you guys tracks by their species. The one I really want you guys to look at is the track with the gold star on top of it. Again, this is where that species changed and the height shot up.
So side by side, we're able to see a numerical perspective of the forest for our baseline year. As we mentioned before, and as you may have noticed on the slide previously, much of the forest was covered by this light purple, and that was representative of one single species, the Cereops decandra. It did predominate the Western Sundarbans and much of Central Sundarbans, and that's represented by those smaller box plots. As you can see, there was very little variation, which was, as we mentioned before, indicative of strong and uniform consistency among the height averages. And then, of course, as Devanshi mentioned previously, those taller box plots are representative of tracks that crossed over a different and much taller species. But overall, the Sundarbans forest as a whole exhibited strong consistency throughout our baseline year.
Taking a look at the visible imagery, at the top left, we have a real scale image photo for reference. And these other 2 images from December 2018 and January of 2019 are NDMI values. The scale on the bottom left of the screen shows us that when the images appear to be bluer, they have greener vegetation or high water contents. And when they are in the red to orange scale, they are drier vegetation with low water content. An important thing to address is that because we are looking at liquid water content, we do get strong returns from the ocean. Another thing is that we also get strong returns from soil deposits or shallow water in the form of dry land. But other than this, we can see a pretty strong pattern for both of these dates that the closer they are to the coastline, the closer these mangrove trees are to the coastline, the higher and greener the vegetation is. So indicating that it's healthier. These are two other dates. And for these two, we decided to do a zoom in. So March 2nd of 2019, and we have May 13th of 2019, and May is taking a closer look at the specific region in the March photo. And what we can see from here is that there is actually healthier vegetation within the conservation forest compared to the urban and farming areas. And this is a good sign that this conservation area is being extremely beneficial to these mangrove trees.
So to conclude, what we found during the baseline year in terms of quantitative data was that in Western Sundarbans, the photon returns showed that the species that predominated that region exhibited consistently uniform average top of canopy height, which indicated to us that the mangroves there had excellent health during the undisturbed year.
And for our central Sundarbans, we noticed that there was variation in the type of canopy averages, but it was solely dependent on, again, our species change within the tracts. So the November 19th, 2018 date and the February 18th, 2019 date were the two ones that I pointed out earlier. And their variance was because of that spike in the other species.
Our NDMI indices, we found that there was not any difference between the species in terms of health. And we also saw that healthiest regions were found along coastlines. Another thing that we saw was there was low seasonal vegetation variability due to our low seasonal climate variability.
So now we will explain what we found during our study year, which was impacted by the cyclone.
We focused on the Amphan supercyclone, which struck from May 16th, 2020 to May 21st of 2020, and it hit in eastern India and southwest Bangladesh, which would be right in the heart of our Sundarbans forest. These are our 2020-2021 indices. They average in the 80s, and we saw that there was 181 millimeters of precipitation, which was the highest for any of the 4 years that we looked, and this was the year with our cyclone.
So over here, we have a before and after of the cyclone Amphan. Our before date was October 12th, 2019, and our after was June 19th, 2020. You can see where those tracks are. That's directly where the cyclone hit, which is super cool. And in this slide, we decided to put them on a box plot. And it is a little more evident in this slide that there was a slight change between the two. As you can see, the total variability was just 0.332 meters. However, we do believe that maybe the satellite could not differ between the healthy top of canopy heights versus barren top of canopy heights, barren from the storm. So that could have altered our data a little bit, but that is just something that we kept in mind.
So these are our real scale images from before and after. We have February of 2020 and November of 2020. Really, the only thing that we can get from here is that there's a large increase of soil and sediment deposits running from and around these islands where our mangroves are located. Now, going into our NDMI values, on our February before photo, we can see a lot of really healthy and high concentration vegetation, not even just along the coastline, really all throughout the forest. But when we go into our after photo, we see this kind of tan orange scale. And what this indicates to us is that this forest is going under high amounts of water stress. And this is due to the cyclone. Another thing to look at would be the amount of soil deposits running down from the land. This would be caused from flooding. And what it does is as it pulls up water, it pulls it all back down into the ocean, and it causes high levels of intrusion within the forest itself.
So in terms of our quantitative data, there was a slight decrease in the average top of canopy heights. However, I did address the challenge that we might have been facing. So we did rely more on our visual imagery because there were more clear changes within that.
Our visual imagery was an excellent add-on to our TOC data. And from our NDMI values, we saw a lot of mass moisture loss. And from this, we could also see some deforestation in regions due to this moisture loss where plants were just dying. And most importantly, we saw a lot of the sediment deposits in these soil runs coming back from the inland down to the ocean.
So taken together, our hypotheses were confirmed. We did say that we hope to see less variability during the baseline year and a lot more during the cyclone year, while the ICESat-2 instrument was unable to see as precisely that decrease in average top of canopy heights. In conjunction with the LandSat-8 data, we were really able to bring out that change as a result of the cyclone. Because of this, our presentation shows that ICESat-2 has high potential combined with other instruments to really capture change to vegetation over time. And as we mentioned before, this is extremely important because mangroves are integral to the health of coastlines, which can be highly populated by many human communities. So it's important that we protect those infrastructures, and we can do so by monitoring the health of mangroves over time.
Some challenges that we did face was with the software and programs. One of our team members had a Mac, and one of our programs was actually not in compliance with MacBook, so it was a little hard to work around that, but we did it. Another thing was finding a purely mangrove allocated region, because sometimes it did look like regular plants were mangroves, but that was not true. So because of that, we actually had to switch countries altogether in the middle of the month, which is another really interesting challenge that we faced. And another thing is that ICESat-2, again, is very traditional in the ice analysis. So any article you might read about ICESat-2 will give you mainly glacier information, stuff like that. So we didn't really have anything to base our study off of, or anything to look after, or to role model against. So that was one thing that we did face doing vegetation. So yeah.
With that, we would like to say thank you for everyone coming out today and watching. We would especially like to thank the SEAS team for making this internship possible and providing all these opportunities. We would like to thank Dr. Simurda, our advisor, for encouraging us to continue our unique project and helping us through the many challenges that we faced along the way. We would also like to say thank you to our audience for coming out, watching us, and supporting us all today. Thank you.
My name is Devanshi Kaura, and the SEAS experience for me was honestly phenomenal. I did so many things that I've never done before. It was so hands-on for a STEM internship that I've done so far. And I have never done anything like this before. And I love my team. Working with them was really, really great. We learned a lot from each other, and it was super fun. And so my future goals, I want to major in biological and agricultural engineering. So working with vegetation in this project was super cool. And who knows, maybe like I'll apply this in college, and I think that's really cool.
My name is Kenna Bernardin. My experience in SEAS was one of the best times I've had in my life. I think this was an excellent way to spend my summer. My favorite part was really my team members. We had a really diverse background of people, and I think we were all able to come up with combining our unique perspectives. And that allowed us to really format our project to our own liking. And despite the challenges that we had to overcome, I think we really made it work. And I think this especially highlights just how important teamwork is within STEM careers and within the STEM field. For my future goals, I want to go into research, and I hope to get a degree in earth science, especially in botany or ocean ecology.
And I'm Isabella Mazzucca. My experience in SEAS was one that surprised me. I definitely thought I had a preconceived notion about what this project might look like, but going into it, I realized that it was not at all as linear as I expected, but I wouldn't necessarily say that that was a bad thing. I really enjoyed that we went through several iterations of ideas, and we had our challenges, especially, pushing the boundary with what ICESat is capable of doing. And I think in the end, that really helped to affirm my interest in engineering. Because as we all may know, engineering also has to deal with a lot of innovation and pushing those boundaries. And being able to step out of my comfort zone, as I did with SEAS, was a huge stepping stone for me. I hope to pursue a major in electrical engineering once I enter college.
Thank you again.